Welcome back, everyone. This is Dr. MAMTamayao-Kieke, and we are now on our third and last lecture for Unit 1-1, Foundational Concepts. In this video, we are going to review basic statistical concepts such as random variables, probability distributions, and random samples. And then we will discuss concepts, principles, and tools relevant to sampling. The third and last part of the lecture will be devoted to the discussion of the most important sampling distributions, at least in the context of this course. Before we start with this lecture's topics, let's first have a review question. What are the 7 steps in designing an experiment? Do you remember? Recall that the 7 steps in designing an experiment are recognition of and statement of the problem, selection of the response variable, choice of factors, levels, and ranges, choice of experiment design, performing the experiment, statistical analysis of the data, conclusions, and recommendations. The first 3 are the pre-experimental planning phase, which is the foundation of an experiment's success. Let's start this unit's lecture with an example. Suppose that an engineer is investigating the formulation of a Portland cement mortar. Suppose further that the engineer added a polymer latex emulsion during mixing to determine if this impacts the curing time and the tension bond strength of the mortar. For this experiment, the engineer prepared 10 samples each for the original formulation and the modified one. The engineer found a very large reduction in the cure time for the modified mortar formulation. However, the engineer has to make sure that this new formulation would not adversely affect bond strength. This table from Design and Analysis of Experiment by Montgomery shows the data on bond strength for the 2 formulations. Before we proceed with the rest of the example, answer this question. In the Portland cement mortar example, identify the following: response, factor or factors, and levels for each factor. So let's look at the answers. The response or responses would be the cure time and the bond strength. The factor considered was the mortar formulation, and we considered 2 levels for this factor, which are the original formulation and the modified formulation. Note that each factor level can also be referred to as a treatment. So let's continue with our example. This dot diagram visually presents the data from the experiment. By visual examination, it may seem that the unmodified or original formulation results in higher bond strength. If you look at the average tension bond strengths, it looks like this impression is supported, as you can see here. However, you can also see a large overlap between the 2 sets of data. So it is not obvious that our perceived difference and the gap between the means is enough to imply that the 2 formulations really result in different strengths. It could be the case that our observation is only true for this sample. It is possible that if we run another sample, we would observe the opposite results. Now, to provide an objective comparison, we can make use of hypothesis testing. But we will discuss that later on. Before we delve into the procedures for hypothesis testing, let's first review some basic statistical concepts. Let's start with basic definitions. Recall that population is the set of all possible elements in a study, while sample is a subset of a population. In an experiment, we cannot state what an outcome would be exactly, but we can define the set of all possible outcomes. And the set of all possible outcomes for an experiment is the sample space. In our Portland cement mortar experiment example, a run is each observation in the experiment. Now, the fluctuations or the difference between runs is the experimental error or simply error or noise. Since this is an uncontrolled and unavoidable error, it is classified as a statistical error. The presence of error or noise reflects a random variable. In our example, tension bond strength is a random variable. More formally, consider an experiment with sample space S, a function x which assigns to each element C of the sample space one and only one real number, x of C equals x, is called a random variable. As for notation, a capital letter denotes a random variable, and its small letter corresponds to one of its values. Now, a random variable can either be discrete or continuous. A discrete random variable is one with finite or countably infinite set of possible values. Now, continuous random variables, on the other hand, are those whose set of all possible values is an interval. There are several ways to present the variability of a random variable. Three of the most popular include the dot diagram, which we use to present the variability of tension bond strength for the two mortar formulations in the previous example. And then we have histogram and the box plot, also known as a box and whisker plot. This looks familiar to you, I'm sure. You may want to review how to manually generate a histogram, but you should also explore functions in Excel and other statistical software such as Stata and R to generate a histogram. A histogram shows the frequency of observed values in a study. It can also give you an impression of the probability distribution of the data, and we will discuss probability distributions in a bit. This is the famous box plot or box and whisker plot. It can be seen oriented vertically like this or horizontally, and you can see a lot of information from a box plot. This shows you an anatomy of a box plot. The box provides the 25th percentile, the 75th percentile, and the mean or the 50th percentile. The end of the whiskers show the smallest and largest data point, usually within 1.5 interquartile ranges from the first and third quartiles, respectively. And you can also show outliers in a box plot. Now let's talk about probability distributions, which describes the probability structure of a random variable. Say we have a random variable y. If y is discrete as depicted in the left figure, the probability distribution of y, say p of y, is called the probability mass function. If y is continuous, as in the right, the probability distribution of y is called a probability density function. In the discrete probability distribution, the height of the function p of y sub j represents the probability, while in the continuous probability distribution, it is the area under the curve f of y associated with the interval that represents the probability. The properties of probability distributions are summarized mathematically here. For discrete random variables, the probability p of y sub j can take a value between 0 and 1. The function p of y equals y sub j is equal to p of y sub j. And third, the summation of p of y sub j over all values of y sub j is equal to 1. Okay? For continuous random variables, f of y takes on a value greater than or equal to 0. And the function p of y within the range a and b is equal to the integral of f of y dy from a to b. That means that the probability of y taking a value within the interval a and b is the area under the curve between a and b. And lastly, the integral of f of y di from negative to positive infinity is 1. Next, we talk about the mean, which is a measure of central tendency or location of a probability distribution. Mathematically, the mean mu is equal to the integral of y, f of y dy, from negative infinity to positive infinity if y is a continuous variable. If y is discrete, a mean mu is the summation of y times p of y all over y. We will be using the concept of expected value a lot. Expected value is the long-run average of the random variable. As you can see, the mathematical representation is the same as that of the mean. The operator E applied to y actually yields the mean mu. Another important concept, the variance, is a measure of the variability or dispersion of a probability distribution. It is usually denoted as sigma squared, and this is obtained mathematically using this formula. As you can see, the mathematical formula implies that the variance represents the average of the squared distance of the observations from the mean. So, we can also represent sigma squared as the expectation of the square of y minus mu. When we see v of y, or the variance operator, this means that we are looking for the expectation of the square of y minus mu, which is equivalent to sigma squared. It will be useful for you to remember the rules of expected value and variance operators as shown. So, the expectation of a constant is just a constant. The expectation of a random variable y is equal to its mean mu. Expectation of a constant times a random variable y is just equal to the constant times the expectation of y. The variance of a constant is of course 0. The variance of the random variable y is equal to sigma squared. The variance of the constant times a random variable is just equal to the constant squared times the variance of y, which is also equal to the constant squared times sigma squared. Next, we have the expectation of the sum of two variables, and this is just equal to the sum of the expectations of the two variables, which is also equal to the means of the two variables. Next, we have the variance of the sum of two variables, and this is equal to the sum of the variance of those two variables plus 2 times the covariance of y1 and y2, where the covariance of y1 and y2 is just equal to the expectation of the product of y1 minus mu1 and y2 minus mu2. Okay, next we have the variance of the difference between y1 and y2. And this is just equal to the sum of the variance of y1 and y2 minus 2 times the covariance of y1, y2. If y1 and y2 are independent, the next rule is that the expected value of the product of y1 and y2 is just equal to the product of the expected value of y1 and the expected value of y2, or mu1 times mu2. And the last one is that the expected value of the quotient of y1 and y2 is actually not equal to the expected value of y1 divided by the expected value of y2. A random sample is one which was selected from a population in a manner in which the selection of each sample is equiprobable. Okay? In practice, computer generation of random numbers can help in obtaining a random sample. Now, let's define a statistic. A statistic is any function of the observations that does not contain unknown parameters. For example, you have the sample mean, okay, expressed as y bar here, okay, which is equal to the summation of all the observations divided by the number of observations n. And then you have the sample variance expressed as s squared, which is equal to the summation of all the square of the difference between each observation and the sample mean divided by n minus 1. And the sample standard deviation, which is the square root of the variance. Now, since the standard deviation has the same unit as the observations, experimenters often prefer to use it. You will encounter the terms estimator and estimate a lot in this course. Now, an estimator is a statistic that corresponds to an unknown parameter, and it is actually a random variable. Now, for example, the sample mean is an estimator of the population mean. Now, before we define estimate, question, what does it mean that the estimator is a random variable? Think about this. Okay, so now an estimate is a value that is computed from the sample data. It is a numerical value of the estimator. So for example, say we wish to estimate the mean and the variance of suspended solid material in Laguna Lake. And we take a random sample of 25 observations, and then we test these observations and record in milligrams per liter the amount of suspended solid material for each observation. Now say that we get a sample mean of 18.6 and a sample variance of 1.2. What do you think would be the estimate of the population mean and the estimate of the population variance? So in this case, it would just be 18.6 and 1.2 respectively. Two of the most important properties of a good estimator are the following. The point estimator should be unbiased, and that means that the long-run average or expected value of the point estimator should be equal to the parameter being estimated. Now, an unbiased estimator should have minimum variance. So it's not enough that the estimator is unbiased. It should also have the minimum variance, which means that this estimator has a smaller variance than any other possible estimator. The following proof shows us that the sample mean is actually an unbiased estimator of the population mean. So what we want to prove is that the expectation of our sample mean will be equal to mu. Okay, so recall that the formula for the sample mean is just equal to the summation of all y's divided by the number of observations. Okay, so we get the expectation of this. And using the properties of the expected value operator, we can just bring out 1 over n because it is a constant. Okay, so now we have 1 over n times the summation of the expected value of y sub I. And now we have 1 over n times the summation of mu. And this is just equal to mu. Now we can do the same thing for the sample variance to prove that it is an unbiased estimator of sigma squared. So again, what we want to prove is that the long run average of the sample variance S squared would be equal to sigma squared, or that the expected value of S squared is equal to sigma squared. So again, we just substitute the formula for S squared here, which is this one, and we get the expected value of that. We bring out 1 over n minus 1, okay? And then we get the expected value of this term. And so now, using the definition that SS, or sum of squares, is equal to this term here, okay? This can be written as 1 over n minus 1 times the expectation of the sum of squares. Continuing, the expected value of the sum of squares would just be equal to the expected value operator applied to the sum of squares. And this is just equivalent to this. And if we recall and perform mathematical operations on the previous term, then we get this, okay? And finally, we get E, or expected value of S squared, is just equal to 1 over n minus 1 times the expected value of SS. And this is just equal to sigma squared. Okay, now we proceed to degrees of freedom. Okay, so degrees of freedom is basically the number of independent elements of a sum of squares. So recall this proof, okay? This number here, n minus 1, is actually what we call the degrees of freedom of the sum of squares, okay? Now, if we look at this, there are actually just n minus 1 independent elements, okay, because we know that the summation of yi minus y bar is actually equal to 0, okay? So the expected value of SS over V is actually equal to sigma squared. V here is the degrees of freedom. Now let's start talking about some sampling distributions. Let's talk about the most important sampling distributions, especially in the context of this course. The most popular of which is the normal distribution, and it looks like a bell as shown. Observations that vary due to experimental error are often described by a normal distribution. And this is why this distribution has an important role in the analysis of design experiments. Now, we use this notation to denote that y is normally distributed with mean mu and variance sigma squared. The probability distribution of y is given by f of y in this equation here, where mu is between negative and positive infinity, and sigma squared is greater than 0. Now, a special case of the normal distribution is the standard normal distribution. If the random variable y is normally distributed, then the random variable z, which is equal to y minus mu all over sigma, follows a normal distribution with mu equals 0 and sigma squared equals 1. Okay, now we're going to look at a very important theorem. It is the central limit theorem, which states that if y sub 1, y sub 2 to y sub n is a sequence of n independent and identically distributed random variables with expectation of yi equals mu and variance of yi equals sigma squared, which are both finite, and x is equal to the sum of all the y's, then the limiting form of the distribution of z sub n equals x minus n times mu all over square root of n sigma squared as n approaches infinity is the standard normal distribution. This basically means that the sum of n independently and identically distributed random variables approximates a normal distribution, and this becomes more accurate as n increases. And since many statistical techniques assume that the random variable is normally distributed, the central limit theorem is commonly invoked. Now let's talk about another important sampling distribution, the chi-squared distribution. If z1, z2 to zk are normally and independently distributed random variables with mean 0 and variance equals 1, as denoted here by NID parenthesis 0, 1, then the random variable x, which is the sum of the squares of all z's, follows a chi-square distribution with k degrees of freedom. And this shows the density function of chi-square. You can see in this graph from Montgomery several chi-square distributions. And as you can see, the skewness differ. The mean and variance are mu equals k and sigma squared equals 2k. As an example of a random variable that follows a chi-square distribution, suppose that y1, y2 to yn is a random sample from a normal distribution with mean mu and variance sigma squared. Then, the sum of squares divided by the variance here follows a chi-square distribution with n minus 1 degrees of freedom. In general, the sums of squares of random variables following a normal distribution divided by the variance follows a chi-square distribution. Now, this is very important and you will see this repeatedly. So please remember. Now, let's look at another distribution that you will be hearing a lot in this course, the t distribution. If z is an independent standard normal random variable and chi-squared sub k is an independent chi-square random variable, then the random variable t sub k, which is equal to this term here, follows a t distribution with k degrees of freedom. This figure from Montgomery shows several t distributions, and the probability density function of t is expressed by this equation. And for k greater than 2, the mean is equal to 0, and the variance sigma squared is equal to k divided by the quantity k minus 2. Now, t becomes a standard normal if k equals infinity. Now, if y1, y2 to yn is a random sample from a normally distributed population with mean mu and variance sigma squared, then the random variable t, shown here, follows a t distribution with n minus 1 degrees of freedom. Now, you will see this again when we talk about hypothesis testing. For the last sampling distribution in this lecture, we have the f distribution. If chi-squared sub u and chi-squared sub v are chi-squared random variables with u and v degrees of freedom respectively, then the ratio fuv, shown here, follows the f distribution with u numerator degrees of freedom and v denominator degrees of freedom. Now, shown in this graph are several f distributions. The probability distribution of x is given by the following. As you will learn, this distribution is very important in the analysis of designed experiments. As an example of a random variable that follows the F distribution, say we have two samples, N1 observations from the first and N2 from the second, and both come from independent normal population with a common variance sigma squared, and S1 squared and S2 squared are the variances. The random variable S1 squared over S2 squared follows an F distribution. Okay, I know that was rather packed. Anyhow, we have covered a review of basic statistical concepts and terms, and we have discussed about sampling and talked about some important sampling distributions. In the succeeding lecture, we will talk about statistical inference. In particular, we will discuss hypothesis testing and confidence interval procedures. Please remember to regularly check our announcement board for new postings, and feel free to send me a message via Ouvlet if you have any concerns. Until next lecture.